Welcome to lecture 24, where we introduce the crucial concept of derivative and differential of a function. Let's first introduce the setting for this definition. So let D be, or let me call this a subset of the real numbers, and let f be a function defined on A with values in R, and let x naught be an interior point of A. And now I will give a brief definition of what an interior point is. So let's say that this is the real line, and on this real line we have a subset A. Okay, so this is the subset A on the real line. Now we say that a point x naught is an interior point if there exists a delta larger than 0, a real number delta larger than 0, such that the interval x naught minus delta, x naught plus delta is entirely contained in A. In other words, we say that x naught is an interior point of A if we can find an interval, an open interval, and this is going to be delta, this is going to be delta, which is entirely contained within A. Okay, we'll come back on this definition later, but for the time being this is enough. X naught is going to be an interior point of A. Now the first definition that we give is the definition of difference quotient. The difference quotient of function f is defined as the ratio f x naught plus h minus f of x naught divided by h, and this is defined at least for h that belongs to the interval minus delta, delta, except of course the point 0. So let me give you a geometric interpretation of this difference quotient, and then we'll come back to the definition. So what we are saying is that we have a function f, and let's say that this is the graph of the function f, and we are now going and pick one point. Let's say that this is the point x naught that belongs to the interior of the subset A where the function is defined. So we see that this is f of x naught. Then we move along the x-axis to a new point x naught plus h. So we see that this h belongs to the interval minus delta delta. This implies that moving from x naught to x naught plus h, we are not going beyond the definition set of A, because x naught is an interior point, so we know that we can find an interval minus delta delta such that all that interval falls within the set of definitions. So we are sure now that this point x naught plus h belongs to the definition set. Now this will be f of x naught plus h. Okay, now the difference quotient is the ratio between this distance So this is what we have at the numerator. Okay, we have fx0 plus h minus fx0. And instead, this is what we have at the denominator. In fact, the difference is exactly h. So the interpretation of the difference quotient is nothing else than the slope of this line connecting this point A to the point B. So we can give this interpretation. This will be the slope of the line through A and B. And now we are ready to give the definition of derivative. Now, the derivative of the function f at the point x0 is defined as f prime of x0, and it is defined as a limit as h goes to 0 of the difference quotient f x0 plus h minus f of x0 divided by h. Of course, this is defined, this is the derivative only if the limit exists and is real. So this is to say that must be a number. We are not accepting this limit to be plus or minus infinity. In that case, we say that the derivative is not defined. Okay? Now, so this is the definition of derivative of a function, but there are other notations, and we'll give these other notations here. So instead that the f prime of x0, sometimes the derivative is also indicated as df divided by dx evaluated at the point x0, or capital df at the point x0, or again f dot of x0. Okay? Now we want to put in relation the derivative with the equation of the tangent. So let's write the equation of the tangent. So if we plot again the function f with the point x0, let's say that this is the point x0, what happens is that when h goes to 0, the point B, this is the point B, this is the point A. So what happens is that the line through A and B gradually becomes the tangent. And let me plot the tangent with a different color. So this will be exactly the tangent. So we can put in relation the equation of the tangent with the derivative, because the derivative is the limit of the difference ratio when h goes to 0. In other words, where the line AB becomes the tangent. So we can write that y is equal to f prime of x0 times x minus x0 plus f of x0. In fact, remember that this is f of x naught, exactly the value of the function at x equal to x naught, and starting from that point, if we move along the tangent, we will follow a line x minus x naught with the slope f prime of x naught. Okay, so now that we have this definition in place, we can define the differential definition of differential. Again, let A be a subset of the real line, and let f be defined on A with values in R, and let x naught be an interior point of A. Then we say that f is differentiable in x naught if there exists a real number alpha such that f of x naught plus h is equal to f of x naught plus alpha h plus little o of h for h that goes to 0. So this is the definition of differentiable function. So let's review this definition. We are saying that f, the function f, which is defined on A, is differentiable in x naught, and x naught is an interior point of A, if there exists a real number alpha such that the function in a new value x naught plus h, which of course is also within the definition set of the function within the domain A. So this function in x naught plus h can be expressed as the sum of f of x naught plus alpha h, where alpha is a real number, and plus an infinitesimal little o of h for h that goes to 0. Okay, now alpha is the differential of f at the point x naught. And now we have a theorem. We say that f of x is differentiable in x naught if and only if f of x has derivative f prime in x naught. Also, we have that f prime of x naught is exactly equal to alpha. So let's prove this theorem, as this will help us understand the strict link between the derivative and the differential. Proof. We will split the proof into two parts. Okay, part 1 is basically this arrow, namely the fact that if f of x has derivative f prime x naught, then f of x is differentiable in x naught, and alpha, the differential, is exactly equal to f prime of x naught. So we wish to prove that f of x naught plus h can be expressed as f of x naught plus f prime of x naught times h plus little o of h for h that goes to 0, which is just like saying that f of x naught plus h minus f of x naught minus f prime of x naught times h is equal to little o of h, which again is just like saying that the limit as h goes to 0 of f x naught plus h minus f x naught minus f prime of x naught times h, all divided by h, this is equal to 0. But this is again limit h goes to 0 of f x naught plus h minus f of x naught divided by h minus, let's apply the algebraic theorems for limits. We see that this is limit as h goes to 0 of h, and we can bring f prime of x0 outside of the limit because it is just a constant. We need to prove that this is indeed equal 0. But what happens, of course, this is divided by h, but what happens, this is just like the definition of f prime, because this says that the limit h goes to 0 of f of x naught plus h minus f of x naught divided by h is just equal to f prime of x naught, because clearly we see that this limit is the limit of h divided by h, which is just a constant. This is equal to 1, and taking f prime to the of x naught to the right hand side, we have exactly this. So this basically proves the necessary condition. Okay, so let's go to the second part of the proof. So this is part 2 now, and we want to prove this arrow. Okay, namely the fact that if f of x is differentiable in x naught, then f of x has derivative f prime x naught exactly equal to alpha. Okay, good. So because we are looking at the derivative f prime of x naught, let's immediately write f prime of x naught, what we would expect this to be. Let's see if this limit exists. Well, this is just the limit as h goes to 0 of f of x naught plus h minus f of x naught divided by h, right? Well, but this can be expressed by using the fact that f of x is differentiable. We can leave h at the denominator, but we will replace f of x naught plus h with f of x naught plus alpha h plus little o of h, and then minus f of x naught. And we immediately see that f of x naught and minus f of x naught, they will cancel each other. So we have limit h goes to 0 of well, by dividing by h, we get exactly what? Well, we have alpha plus little o of h divided by h, but clearly this is just alpha. So we proved not only that this limit exists, so the function has derivative, but also that the function derivative is exactly equal to alpha. Now, just this is a note for the future. The equivalence between derivative and differential is not present in functions of two or more variables. So what I'm saying is that we have just proved that the derivative of a function of one variable is just like having the differential, so they are totally equivalent concepts. Well, this equivalence doesn't hold if we consider function of more variable, which we will consider later on in the course. We'll pass now to the geometrical interpretation of the differential. So what we would like to interpret is the expression of f x naught plus h as the sum of f of x naught plus alpha h, where alpha is the differential, plus little o of h. Okay, so let's plot a function and see if we can give a geometrical interpretation of this expression. Let's say that this is our function f of x, and we start from a point x naught, and then we move to a new point x naught plus h. Okay, so we know that this is f of x naught, we know that this is f of x naught plus h, right? And now we want to give a geometrical interpretation, so let's start by calling this point P and this point Q, right? So, or let me use S for this point. So immediately we can write f of x naught plus h simply by ps. So this is the segment that represents f of x naught plus h. And now we can first identify a point Q, which represents exactly f of x naught, so we have pq. Clearly we want to express now qs, this segment qs, as the sum of alpha h plus little o of h. But remember that alpha is nothing else than the derivative, so we know that the derivative at this point is nothing else than the slope of this tangent. So there we go, we have another point R, and we say that alpha h is nothing else than QR. Yes, because basically alpha is the slope of the line tangent at the point x naught. We know that the increment is h, we know that this is h, so if we multiply h by the slope we get exactly the segment QR. So finally, we have our S. So we are now in the position to say that a function f is differentiable in x0 if when h goes to 0, the segment Rs that we have just identified on the graph goes to 0 faster than QR. So we are saying that this segment Rs, which correspond to little o of h, so this needs to go to 0 faster than the segment QR, which is exactly this, and in our case is alpha h. In fact, if we say that Rs is little o of h, that implies that Rs goes to 0 faster than QR. So this is the geometric interpretation. We can say that a function f is differentiable if by identifying these two segments QR and Rs, we see that Rs goes to 0 faster than QR. Right, so now that we have all our definition in place, we can start applying this definition to a number of elementary functions. So what follows is just a list of the derivatives of elementary functions or at least some of them. Okay, let's start with the first function f of x equal to x to the square. Okay, and this function clearly is defined on a the entire real line. Okay, now we can use the definition of derivative or the definition of differential because we know that they are totally equivalent. So I'll call with 1 the use of the definition of derivative, and with 2 the use of the differential. Okay, so let's start with f prime x naught. Now of course x naught can be any real number, and we know that this is equal to the limit as h goes to 0. Remember that we have to write a difference quotient that in this case becomes x naught plus h to the square minus x naught square all divided by h. Well, but this is equal to limit as h goes to 0 of x naught to the square plus 2x naught h plus h square minus x naught square all divided by h. Immediately we'll simplify these two and we have limit h goes to 0 of 2x naught plus h. But when we take the limit as h goes to 0, we are left with 2x naught. So this is the derivative. Let's see if this is consistent with the second approach. Okay, in the second approach, we will try to express f of x naught plus h with a differential. Okay, now of course if we know that f is x to the square, this is just like saying x naught plus h raised to the square, which is equal to x naught square plus 2 times x naught h plus h to the square. And we recognize that this is f of x naught, because f of x naught is exactly x naught to the square, plus alpha, which is exactly 2 to the x naught times h, plus little o of h. So yes, we have just proved that alpha is just equal to 2 to the x naught. Okay? Okay, let's move to another function, function 2. Let's take f of x equal to x to the cube. Once again, a is just equal to the entire real line. If we apply the definition of derivative, we get that f prime of x naught is the limit as h goes to 0 of x naught plus h to the cube minus x naught to the cube divided by h, which is limit h goes to 0 of x naught to the cube plus 3 times x naught square h plus 3 times x naught h square plus h to the cube minus x naught to the cube. We can immediately simplify this and that, and we have now limit h goes to 0 of 3 x naught to the square plus 3 x naught h plus h to the square, which clearly leaves us with 3 x naught to the square. Let's apply the second method. F of x naught plus h is x naught plus h to the cube, which is x naught to the cube plus 3 x naught to the square h plus 3 x naught h to the cube plus h to the cube, which we can rewrite as x naught to the cube plus, we have 3 x naught to the square h, and this final thing, this final expression, well, we can just reuse the original expression because we can immediately recognize this to be f of x naught. F of x naught is x naught to the cube. Plus, we have alpha, and alpha, of course, is now simply 3x naught to the square because this is the only coefficient of h, and what remains is nothing else that little o of h, because we recognize that in both cases we have, sorry, this was just a square, just realize I made a mistake here, this was the square, but we immediately see that these last two terms, being the h to the square and h to the cube, both are little o of h. So this concludes our proof that alpha is just equal to 3x naught to the square. Okay. Maybe a little bit more interesting would be the derivative of e to the x. Once again, a is the entire real line. Okay, first definition. F prime in any point x naught is equal to the limit h goes to 0 of e to the x naught plus h minus e to the x naught divided by h, right? And we see that we can factor out e raised to the x naught at the numerator. So we have e to the x naught times the limit as h goes to 0 of e to the h minus 1 divided by h, But remember that this is one of the fundamental limits, so we see that this is simply e to the x naught. Second approach, f of x naught plus h. Well, this is e to the x naught plus h, which is e to the x naught times e to the h. And if we now apply the short expansion of e to the h, we have e to the x naught times 1 plus h plus little o of h. And multiplying out, we get e to the x naught plus e to the x naught h plus little o of h. Once again, we recognize easily this to be f of x naught, this to be alpha, so alpha is just e to the x naught, which is consistent with what we found with the first method, plus little o of h. Good. Sine function. What about the derivative of, sorry, this is number 4. F of x equal to the sine of x. Again, a, the entire real line. So we can now compute the derivative in any point x naught. So f prime x naught limit as h goes to 0 of sine of x naught plus h minus sine of x naught divided by h. Okay, and now let's apply the addition formula for the sine. We get limit h goes to 0 of sine of x naught cosine of h plus sine of h cosine of x naught minus sine of x naught. And now factoring out x naught, you see these two terms, this term and this term, right? If we factor out sine of x naught, of x naught, that multiplies cosine of h minus 1 divided by h plus limit h goes to 0. Of course, now we have cosine of, well, we can factor out cosine of x naught in this case, right? So we can have cosine of x naught here times the limit sine of h divided by h. And now applying what we know about the fundamental limits, if we multiply and divide the first, let me do this. We recognize that this cosine of cosine of h minus 1, well, we need basically an h at the denominator to find some of the fundamental limits. So I'll do this. I'll divide by h and multiply by h. And now you see that this is becoming sine of x naught times the limit h goes to 0 of cosine of h minus 1 divided by h squared times h plus the cosine of x naught times the limit h goes to 0 of sine of h divided by h. But clearly we see that this we know is just 1, and instead we know that this is 1/2. However, this So this will tend to 1/2. This will tend to 0. So we are just left with the cosine of x naught. So this is the final result for the derivative of the sine function at the point x naught. Let's follow the other approach to compute the same derivative. So we need to find f x naught plus h, which is sine of x naught plus h, equal to sine of x naught cosine of h plus sine of h cosine of x naught, equal to. Now we will use the short expansion of the cosine, and we have sine of x naught that multiplies 1 plus little o of h, and then we have plus cosine of x naught. Let's expand the sine. We have h plus little o of h, and this gives sine of x naught plus cosine of x naught times h plus little o of h. So this is simply f of x naught. This is alpha times h, so alpha is the cosine of x naught consistently with the other approach, plus little o of h. Good. Let's move to example, the function 5. Let's take the logarithm of x, and now a is just the or plus, okay, just considering only positive numbers. Okay, so when we apply the derivative, we of course we refer to only the positive number. Now let's follow the second approach first. So let's try to evaluate f of x naught plus h, and then apply the one after. Okay. So f of x naught plus h is the logarithm of x naught plus h, which we can rewrite as the logarithm of factoring out x naught. We have x naught times 1 plus h divided by x naught. And remember that h is very small. Okay, we can just apply now the properties of the logarithm. We can rewrite this as logarithm of x naught plus the logarithm of 1 plus h divided by x naught. But remember that we are in the context of very small h, right? Because h is something that goes to 0. So we can now use the expansion of the logarithm as follows. We can write logarithm of x naught plus, we have simply 1 divided by x naught times h plus little o of h. So we recognize this to be f of x naught is just the logarithm of x naught plus alpha times h plus little o of h. So our conclusion is that f prime of x naught, where x naught is any positive real number, is simply given by 1 divided by x naught. Of course, this was x naught. Okay? Let's see if we find a consistent result by following the first approach, namely the definition of derivative. We have limit, so let's write f prime of x naught as the limit as h goes to 0 of logarithm of x naught plus h minus logarithm of x naught divided by h. Okay, and this is equal to by just doing the same factorization, limit h goes to 0 of we have logarithm of x naught times 1 plus h divided by x naught minus logarithm of x naught equal to limit h goes to 0 of logarithm of x naught plus logarithm of 1 plus h divided by x naught minus logarithm of x naught all divided by h. Let's move down a bit. We have now limit h goes to 0. And we see that this and this, they will cancel out. And now what we can do is what we need. I mean, we recognize that there might be a fundamental limit in this expression. So we might want to have x naught here, which is just like saying multiplying by x naught here. Right? Now we see that we have the logarithm of 1 plus h divided by x naught divided by h divided by x naught. And this, of course, is all multiplied by 1 over x naught, which is just a constant. And we see that these limits is clearly 1 with an easy change of variable y equal to h divided by x naught. Okay, so yes, we finally have that this limit is 1 over x naught, which is exactly the same result that we had before. Function 7, no, sorry, this is function 6. F of x equal to 7 to the x. First approach. F prime, of course this is defined over the entire real line. F prime in x naught, limit as h goes to 0 of 7 to x naught plus h minus 7 to the x naught divided by h. Factoring out 7 to the x naught, we have limit h goes to 0 of 7 to the h minus minus 1 divided by h. But we know that this is simply the logarithm of 7. So we finally have 7 to the x naught times the logarithm of 7. And we'll leave as an exercise to apply the second definition of differential to find the same result. In conclusion to this conclusion, we notice that the fundamental limits, the short expansions, and the derivatives of elementary functions are exactly different way of expressing the same concepts. In fact, when calculating the derivative of elementary functions, we made extensive use of both fundamental limits and the short expansions.